So if there's anything dramatically wrong, please also put that in your comment box. But for now, appreciate the opportunity to show you a little bit about some things going on with dense geophone arrays lately. And I'll trust that there are a number of you out there listening to me. So a couple of the arrays that I'm going to talk about are shown here on the title slide. One of them that I'll talk about at the beginning is focused on volcanic processes around Mount St. Helens, and then the other is looking at a much smaller scale, about a 700-meter reach of the Trinity River in Northern California. So those two topics, the first one, a hybrid passive and active source seismic study at Mount St. Helens, will be the first thing I talk about. And then I'll look at an environmental seismology example from the Trinity River Restoration Program. And the third thing that I'll touch on very briefly is actually teleseismic imaging with geophones, and maybe how their role might evolve in the near future. So why geophones for this presentation? They're pretty simple instruments. They've been around for a long time. They're very low power, just a passive mass spring system. So the sensor itself doesn't require power. They're cost effective, certainly compared to force feedback sensors, which are usually at least an order of magnitude more costly. And they're durable and easy to deploy. And so all of these strengths are really geared toward allowing us to use lots of them. So in many recent sort of views of using these geophone arrays, they could be referred to as large N arrays, or perhaps part of the IRIS wave fields initiative to get past spatial aliasing of the wave fields that we use in seismology. And if we're going to do any of those things, they just require lots of sensors to increase the spatial coverage of the wave fields we want to study, but perhaps sacrifice some things. The things that would be sacrificed would be, say, sensitivity to low frequencies. That's a little bit arbitrary depending on the natural frequency of the geophone and how strong the signal is. Very strong signals, we might be able to work well below the corner frequency of the geophone. I'll mention that a little bit later. The other weakness is that we're often interested in long time series, and many of the quick deploy recording packages that contain geophones have much shorter recording lives than we're used to in, say, broadband seismology. And just if you're just to make sure we're all on the same page, a geophone really is essentially just a mass on a spring, a conductive coil around that inertial mass, and it's moving over a magnet, so it's generating current proportional to the velocity of the movement of that mass. And so it's a pretty simple signal to measure, but it will have a finite response and have a decaying sensitivity below the natural frequency of the instrument. So the first example from Mount St. Helens, this one is sort of opportunistic as a hybrid passive and active source array. And so in the past, for the most part, the passive and active source seismology have kind of used separate equipment when they go out in the field and then sort of compared afterward. And I think there's a lot of room for more overlap there. And I think that's something we're seeing from a number of groups in recent years. The example that I'll look at is possible because of the iMUSH project, which is a large and multidisciplinary project with components beyond seismology, but I'm gonna focus on the seismology today. So there are seismic investigators from the University of Washington, Rice University, Cornell, USGS, and then University of New Mexico was a late addition to this seismic experiment. And we did this through collaboration and rental from a service company, Nodal Seismic of Long Beach, California. And so the big figure that you're looking at shows the nested seismic arrays that were part of the iMUSH project. And the broadband sensors are in the orange triangles there, about 10 kilometer or so spacing. The parts that I'll focus on more will be, say, the black dots, which were the first deployment of the Texan geophones. Those data we won't look at too much. They recorded mainly just during the times that the shots went off. So the black geophones recorded the shots that were the blue stars. And then all of those black dots were moved. Those instruments were moved to become the red dots in a second geophone deployment that was set out to record the shots that are in the cyan stars here. And the component that I'm mostly going to focus on is right in the middle, the purple dots that kind of make a spider web sort of shape are the nodal sensors. And so the nodal seismometers are just one type of seismograph that has an internal geophone, and I'll describe those coming up next. The main motivation for using the nodes here was to really leverage the active source project that was already planned. If we could get these instruments at greater density right up by Mount St. Helens, then they'd benefit from recording both phases of shooting rather than moving the stations away in the second phase of shooting. And so we knew this would amplify the analysis of the active source data, and then it was a little more exploratory to look at what we might get from the continuous data at times other than the active source shots. So the instruments used in this case, some people will call them autonomous seismographs or nodes. They're cable-free seismographs, meaning that it's a complete recording package. So this sealed recording package has a GPS clock so that the timing does not drift, 24-bit digitizer, so it has good dynamic range. The ones that were used for this experiment had a 2-week battery life. The newer models have a 1-month battery life, and they have the hard drive capacity to be able to record continuously for that whole time. So they could store, say, at 250 or 500 samples per second, the data for their entire battery life. And in this case, the instruments were rented from Nodal Seismic, an oil and gas service company from Long Beach, California. The array that was deployed took advantage of the wilderness trail system at Mount St. Helens and the adjacent logging and national monument roads. About 900 nodes recorded continuously for 2 weeks at 250 samples per second. You can see some of the longer term stations of the Pacific Northwest Seismic Network and Cascades Volcano Observatory are shown in the other symbols, the triangles and the squares here, but the nodes are all of the black dots with the white halos. So essentially all of them within about a 12 or 15 kilometer radius of Mount St. Helens. So I'm going to talk in a couple different parts. One, to take a look at what we're learning, what we can do with some of the continuous data to study microseismicity at Mount St. Helens. And then a second example of where having the nodes was a boost to the active source component of the experiment. So for the first one, a good way to start is to look at about 2.5 minutes of data here. So as you look from the top down on this screen is time increasing through that 2.5 minutes. And we've just arranged the node seismographs from left to right by distance from the summit crater. And most of these events are occurring right beneath the summit crater. So this is essentially a distance from event. And the seismograms are just shown as colors, where red colors would represent positive or upward velocities, and negative or blue would represent downward velocities. And we can see pretty clearly what some of the events, the 5 events in this cluster from the PNSN, the Pacific Northwest catalog, how those would look. They're pretty obvious on the node array. And then we were kind of confronted with, well, how are we going to approach this for a couple of weeks of continuous data to pick every little earthquake beneath Mount St. Helens? Could we use this array to take a more objective and perhaps more automated approach to detecting and locating microseismicity? And so what I'm going to show here is mostly the work of Steve Hansen, who is a postdoc at UNM and now on the faculty at Macquarie University. And so what he implemented to detect and locate microseismicity at Mount St. Helens was a reverse time imaging approach. And we did a little bit of pre-processing to do this. First turn of the seismograms into STA, or short time average over longer time window average, STA over LTA functions. And those basically just show us changing variance in the seismogram. And instead of looking at those on individual seismograms, what we did is to apply reverse time imaging, so that we were essentially treating the seismograms as speakers, so that they would play back their recordings into the subsurface. And that's what you're seeing over on the right, is this expanded window of about 20 seconds being played back into the subsurface. And where that subsurface energy reaches a maximum in spatially and temporally, you get one of those big plus signs that expands and then parks in the location of the maximum. And so those are what we take as indications of an event taking place. And so we automatically get an estimated origin time and location for that event. And the events, the first two in this sequence that are shown with the red triangles here, these are events that were not detected by the PNSN network, and the black triangles show events that were. And where the same events were detected, the locations were quite consistent. And the events that were only detected by the nodes mostly showed up concentrated in similar locations. There is a bit of tuning to figure out, what constitutes an event, what constitutes a detection. And so in this case, we used time randomized traces to establish a noise level above which we could confidently declare detections. So just to zoom in on one of those as a still frame snapshot, this is what a back projection of a magnitude approximately -0.2 earthquake looks like right beneath Mount St. Helens. And so you can see the array is able to localize the origin of this very small earthquake within about 1 to 2 kilometers beneath Mount St. Helens. Usually there's a much more sharply defined maximum in the horizontal dimension than in the vertical, just because we only have vertical component geophones, so we don't have S-wave arrivals. And in the horizontal dimension, we have the events surrounded with 360-degree azimuthal coverage, so the horizontal position is pretty tightly constrained. So without any picking at all, we get this catalog out of the reverse time imaging approach. And if we just look at the spatial distribution of the catalog, this is what we see here on the left in map view. These boxes are all 500 meter pixels. So the reverse time imaging volume was a 10-kilometer cube made out of these 500 meter pixels. And so the greatest concentration of events clusters in 1 or 2 500 meter wide pixels, basically beneath the summit crater of Mount St. Helens. The dots on this map are the white dots are the locations of the inner ring of geophones, the innermost part of the Mount St. Helens Wilderness Trail System. If we look in a cross section from east to west, so this would be going right through the middle of Mount St. Helens from west to east. The distribution of seismicity is shown here in the cross section, and so we see this pretty focused subvertical column of seismicity just slightly on the eastern edge of the summit crater. So we can automatically derive this catalog, which had a little over 200 earthquakes in it, and then have a good starting point for thinking about how this might relate to things like the shallow parts of the magmatic system. Just for reference, the green line is where the shallowest hypothesized magma chamber was from past studies. We definitely see seismicity going up and through that. And And then the greater volumes of magma are thought to be deeper than about 5 kilometers beneath Mount St. Helens. So most of these earthquakes, these are the kinds of things normally going on at Mount St. Helens, and we're kind of looking at how could we detect these in an automated fashion and objective fashion using the dense array. And we've kind of moving on from there. What we'd like to ask is, are we seeing any unusual events with the node array compared to what's typically picked up at Mount St. Helens? And so that's where the next topic on microseismicity goes. And it's to look at some potential identification of shallow or not extremely shallow. I'll be more specific about the depths later, but upper crustal, say uppermost 5 or so kilometers, low frequency earthquakes at Mount St. Helens. These low frequency earthquakes are typically observed in great abundance during volcanic unrests and eruptive events, but are not typically seen during quiescent time periods at Mount St. Helens and are less frequent or very rarely observed at during quiescent times at other volcanoes. So to give you an idea of what a low frequency earthquake is, we'll compare it to what you could call a normal earthquake, if you like, or in this setting, a volcano-tectonic earthquake, where we'd see a very impulsive start to the event, an impulsive P arrival, an impulsive S arrival a little bit later. The duration of the event appears to be pretty short. This impulsive P arrival amplitude tapers off, and then on the horizontal channels, we pick up the S arrival a little bit later. And this red bar is a 3-second time window. Over on the right, looking at a low frequency event that was recorded at Mount St. Helens by this array. The red is also a 3-second time window, and so you can see that this event lasts a lot longer. It's also dominantly composed of low frequencies, so it's very depleted in energy above about 10 hertz, whereas the VT events, we could see those at Mount St. Helens going up to 100 hertz sometimes. We can see this a little better in a spectrogram view. And what's notable about this comparison between a VT and LF earthquake is that these earthquakes are in about the same location. So based on the reverse time imaging, the horizontal locations were within 500 meters. The depths are more uncertain, 1 to 2 kilometer uncertainty on the depths. But both of these were estimated to be about 2.5 kilometers below sea level. So pretty close to each other. Most of the path is the same between each of these events and the seismometers that recorded them. So on the left, we see again this impulsive beginning of the VT event. So here time is increasing downward and frequency is increasing from left to right. And these spectrograms are a little bit unusual perhaps, or processed in that what we've done is remove the median spectrum over this 5-minute window. So what you're seeing is signal in excess of the background spectrum to sort of take out the shape of the background noise. And so you could see the VT event excites everything from 1 to 100 hertz, and the amplitude tapers off relatively quickly in time compared to the LF event on the right, where you can see that it's a little bit more of a gradual onset. There's much lower power above about 10 hertz, and the event appears to last quite a bit longer. So these are just to give you a feel for the distinctions between the VT and LF events. And LF events generally weren't thought to be going on at Mount St. Helens in 2014 when we put this array out, and student Margaret Glasgow at UNM was noticing that actually a good chunk maybe of the detections we were seeing, a couple events a day or so, were actually these LF events. They weren't all VT events. We needed to dig into this a bit further in that there are a number of sources of LF seismicity or LF ground shaking signals that you could see at a volcano. And so some of them could be things like rockfall. And so some of the signals that we were thinking were LF events were reported as possible, but not really known rockfall signals. And so what we're doing here is using beamforming with a dense cluster of the node stations to take a look at the slowness or the inverse velocity of the wavefronts of the arrivals of these signals. And so for a rockfall event, we get a very slow arrival, so a slowness that plots farther from the center in these beamforming plots. Whereas for the LF events that we were seeing pretty frequently, many of them came in with pretty small slownesses, or to turn this around into velocity, they would have apparent velocities of 7 to 11 kilometers per second, which is much faster than the upper crustal velocities at Mount St. Helens. And so these things have to be coming from below and approaching this dense subarray that way. So in this case, the density of the geophone array was very helpful for distinguishing between a solid Earth and an environmental source. And even after looking at the slownesses with beamforming to confirm the locations of these events, we ended up with about 2 events per day that were LF events that were in the subsurface between about 0 and 5 kilometers depth. And so if we look at those in map view, these are relative relocations from Geophone at a postdoc at University of Washington. And the main thing you can see is that the VT earthquakes, the red ones, and the LP or LF, long period or low frequency earthquakes, the yellow ones, are mixed in a similar volume. There is some width to their distribution. They're not in exactly the same place. But many of them are, many of the LF events are nearly co-located with VT events. A lot of times when low frequency seismicity is seen at volcanoes, it has a harmonic spectrum. The dense node array with 360-degree azimuthal coverage offers a nice chance to look at the displacement spectra of these events, at least the vertical component spectra. And over on the right, the observational spectra are in the black and the green lines. The difference between the black and the green is just the length of the window. It doesn't change the spectrum much, so we can sort of leave that alone here. And then the solid orange wide line is just a simple prediction for a shear failure, sort of Brune style source spectrum. And so these spectra can be fit pretty well by assuming they were similar to normal earthquakes, but they just have anomalously low corner frequencies, which is quite a bit different than if we were to look at, say, other sources of LP seismicity that are seen at volcanoes. So on the bottom here from Shuei and Matosa, this is obviously a very different type of signal. This is for a degassing burst at Kilauea. And in this case, you get a strongly resonant spectrum with sort of order of magnitude relief between the harmonic spectral peaks and the intervening troughs. That's definitely not the kind of thing we're seeing at St. Helens. So there's some interesting low frequency seismicity going on that's mixed up spatially with the high frequency seismicity. And this is something we're keen to look at a little bit further. I shouldn't do that. Sorry about that. Just a curiosity. So our next step on the source studies is to use the next generation of node equipment. In that, to do more detailed source studies, we'd really benefit from having 3-component data so that we can more reliably analyze S waves in addition to P waves. And we'd also like a longer recording duration. And at Mount St. Helens, if we're going to sample the whole lower hemisphere of these events, we would need some sampling essentially above these earthquakes. And so last fall, in collaboration with Amanda Thomas at University of Oregon and Wes Thalen and Seth Moran at USGS CVO. We installed a new array of nodes for 1 month around Mount St. Helens. I should say that about a third of the nodes in here came from the Iris Pascal facility. The others were from Amanda Thomas at the University of Oregon. And we had a ring of about 90 of these around the base of the mountain at treeline, a dense array off to the southwest to reoccupy the array we used in 2014, and then 2 dense arrays of nodes, one on top of the dome in the summit crater and the other on the crater floor in the breach at the northern end of the summit crater. And so we're just starting to analyze those and hoping to be able to use the nodes, in this case, to start doing source inversions at much higher frequencies and with 3 components to get at these low magnitude but obviously distinct mechanisms of seismicity going on beneath the summit crater at Mount St. Helens. So the second example for Mount St. Helens, I'll go through quickly, but we were able to get an interesting boost to the active source analysis. So if we were looking at an offset gather of the shots at Mount St. Helens, we could see a few different things in those. What we've done here is just sorted the shot records in distance bins, and so these are just in 1 or 2 kilometer distance bins. You can see the big P wave arrival and S wave arrival. The way these are shown is not the raw seismograms stacked themselves in the bins, but again the STA over LTA functions. So they show us when there's basically an increase in power again in the seismogram. And where that turns out to be helpful is down here with this later arrival at about 12 or 13 seconds that has that starts off flat and then starts to bend, sort of taking on this hyperbolic shape that we'd expect. What I didn't tell you about this first figure, this one here, is that it's using only the shots from the east side of Mount St. Helens. Whereas if we actually do the same thing with a stack of all the shot records from the west side, this PMP arrival disappears. The PMP arrivals were not really expected to work well in this active source survey because there's such a long coda from all of the shots. The P wave coda can last for 20 or 30 seconds after a shot in a volcanic environment like Mount St. Helens. And so it takes quite a high density of data to be able to see through that high scattering energy in the coda to pick up the PMP energy. And so what we're able to do with that is see some spatial variations in the reflectivity of the Moho. And I think you can see that a little better by looking at individual shots as they were recorded by all of the node seismographs. And so if we look at the shots outlined in blue, these 3, and we make an NMO or a normal move out corrected stack. This is a median stack. Each one has about 1,500 seismograms in it, or 1,500 STA, LTA functions for that shot record. And you can see a pretty clear peak for the Moho at about 42 kilometers in each of these. So a strong P reflection off of the Moho. If we go just to the other side of Mount St. Helens, and remember the node array is only about 25 kilometers wide. If we go to the other side and look at the records of these reflections, again, they're medians of about 1,500 STA, LTA traces, but there's no discernible Moho. So how is this disappearing? How are we going from a full reflectivity continental Moho on one side of Mount St. Helens to nothing on the other? Or how can we get a better view of that at least? So what we're able to do, given the density of the stations and the sort of aerial distribution, is that we could map out on the lower right the reflectivity of the Moho as a function of position around the array. It's really best resolved beneath the node array, so sort of in this neighborhood. And we see this sharp boundary. The dashed line here is actually the St. Helens seismic zone location, which is a right lateral deformation zone, seismically active deformation zone, and also geodetically apparent deformation that allows the coastal block or forearc region of Cascadia to move northward with respect to most of the arc. And so the change in Moho reflectivity seems to be located along that transition. The white circles here are the deep long period earthquakes at Mount St. Helens. For this talk, I'm mostly trying to show the different technical abilities rather than get into the interpretations for this. But in this case, what was useful is that we could get to this abrupt change in reflectivity of the Moho, and that it had to be happening over a very short distance. So it looks like it's likely compositionally controlled. One way that we could get some insight into the compositions that would be present is to compare with thermal models. So this is a thermal model from Ellen Syracuse for the Central Cascades. And what we've done is just shade in the serpentine stability field, or really antigrite stability field here. And so to potentially be imaging the edge of this cold and hydrated nose of the subduction zone wedge seems at least plausible, in that the thermal models would predict that the edge of the antigrite stability field would be pretty close to Mount St. Helens. And something like a phase change, a sharp phase change boundary could possibly explain the disappearance of the Moho here. So these are a couple of the things that we've been able to do with the St. Helens data. So for this hybrid passive and active source array, the main thing I'd stress is that if you're designing an active source experiment, it's definitely worth thinking of how to take advantage of a little longer recording duration, a couple weeks or a month, especially if it's a seismically active area like a volcanic field. But perhaps it could also be of interest even for environmental processes if there aren't tectonic or magmatic earthquakes going on in that location. The high station density is long been known to be key for active source experiments. And with that high density and multiple shot distances and azimuths at St. Helens, we were able to see through the high scattering environment to pull out PMP reflections, which turned out to be useful for characterizing the deep crust and upper mantle structure. So the second part that I want to talk about is a very different example, and there are many ways that people are using these sorts of geophone arrays now. And so I just wanted to show one environmental example. And this really builds on the idea of using seismology to listen to fluvial processes. And what I'm showing here are just a couple of what I would call a pioneering observation on the left and analogous modeling effort on the right. So on the left is just the background noise spectrum through a year at the Trinity River in Nepal. So a very high stream power setting in the Himalaya. And what they're showing is that there's this hysteresis that essentially shows that for a given water level, take 3 meters here, you have something like 4 decibels higher power at the beginning of early in the wet season relative to the same level of discharge later on in the year. And so the interpretation, and which is favored by field evidence also, is that you're just getting more bed load transport at the beginning of the wet season for a 3 meter stage level in the river than you are at the end. There may be other features like changes in bed roughness that could contribute to hysteresis. It doesn't necessarily have to be all bed load, but it's about the same amount of water in the river and a much stronger signal at different times of the year. So this really launched people in the direction of trying to figure out how to use the signal. And over on the right is a prediction of the seismic signal 600 meters away from a river. This is an analytic model of Hertzian impacts from Tsai et al. 2012. And so since this time, there's been sort of a building interest and some encouraging results in terms of seismology's ability to constrain bed load movement. Where I've worked on this, I started using some L22 seismometers in these quick deploy recording packages from Pascal. These were very handy. The L22 is a 2 Hertz geophone. It's a 3-component geophone, so a nice instrument. And in here, in these recording boxes, we'd have the GPS clock and a RefTech data logger and and we'd include a 30 amp hour battery, and that along with the solar panel, we could record for a long duration out here. And we focused on this controlled flood in Grand Canyon. In this case, we put out several, I think 7 or maybe 9 seismometers. At the Trinity River, which I'll focus on here, we used the nodal seismographs and deployed a dense array to investigate the spatial variability of the signals coming from the river. And we did this in another controlled flooding setting at the Trinity River in Northern California. So just to introduce this very briefly, the Trinity River, which is located in Northern California, the discharge is regulated by a dam. This is part of a restoration program that's really aimed at salmon fishery restoration. The key for now is really that there's an unusual amount of gravel left over from hydraulic mining in the 1800s, and the river did not have much discharge since the dam was in place. So there was limited ability for natural channel restoration. And so they're trying to basically stir up the gravel by simulating storms once per year in order to improve the salmon fishery. And I've been working on this in collaboration with Dave Guyman and Robert Stewart at U.S. Bureau of Reclamation. And so the focus here, just to get everyone on the same page, is bed load. We're talking about the coarse sediment, in this case gravel, that's sort of rolling, sliding, bouncing along the bed. And so these impacts of rock are an important part of the sediment budget. They're key to this salmon fishery restoration, understanding how bed load is moving. And it's very hard to measure bed load transport. And the simple reason is that it's hard to measure at the bottom of a river while it's actively being carried away. And these collisions of rock should be a tractable target for seismology, as we expect them to produce elastic waves. So why we'd look at the Trinity River? We have this controlled setting where floods are going to happen at known times, and they'll take the discharge from low values of just a few tens of cubic meters per second up to a few hundred. And so there's a chance to record that and the river's response to it. They're also injecting gravel. So in this case, we could have the chance to look at supply perturbations during a high discharge experiment. And while the experiment's going on, they do multiple bathymetric surveys by running jet boats up and down the channel. So this is a place where they're really focused on trying to understand bed load movement. And so a nice place to take a look at what seismology could record, and if we could actually see, variability at sort of the reach scale in rivers. Just to give you an idea of some of the observations that they have at the Trinity River, this will show you what the flood looks like at the time that we're observing it seismically. So this is a physical sampler, sort of the open end of this box that we're looking down at would sample or collect bed load as it moves down the channel. And this is showing it at 3,300 cubic feet per second. The flood that we were looking at was operating at about this discharge, about 8,000 cubic feet per second. And so you can see this is well above the critical shear stress, and there's lots of bed load moving, including instant replays of a large clast being rafted down the channel on top of finer gravel. This is probably a more informative view where you could see right at the threshold of movement, maybe it's around 16 tons per day being transported, whereas up at the level of the peak of these floods, it's about 1,000 tons per day being transported. So what we want to do is look right around the injection point, this red star, and we have this sort of corridor of seismometers, node seismometers, spaced about every 30 meters along the channel, and also some sensors radiating away from the channel to constrain attenuation of the signal. We had one broadband 3-component sensor in the middle of the array. So just to give an example of the kind of thing that we could sort out with this experiment, because we have a convenient setting of constant discharge while the gravel supply is augmented. So this blue line here is the constant discharge at the peak of the flood. And then the time periods of gravel injection are shown as the dashed black lines. And so right after gravel injection, you have very high power because there's a much higher transport rate for the gravel. And then the power actually declines and gets back to a baseline value for that discharge within about 10 hours after these events. And that's something they've been curious about because they started off running these events for multiple days. And they were wondering, how long does it take to effectively mobilize an augmentation of gravel supply in the river? And so the temporal resolution from seismology here is something that shows them something that they weren't able to see in the past and affects some of the planning for future floods where it may not be necessary to run the river at high discharge as long because we can see how the river responds. We could also do things like try and pick out what the bed load spectrum looks like compared to the water flowing spectrum. And so here the spectrum during time period S2, sort of peak of water and gravel transport, shows very high power across the whole range. S3 has identical discharge, but just much lower gravel transport. So the difference between S2 and S3 really shows us where the part of the frequency spectrum that's responding to bed load augmentation. So we know then that we can focus on the high frequencies, something like greater than about 20 hertz if we want to characterize bed load movement. So if we open this up and look at the low frequencies separately here, we see that they're pretty smoothly correlated. These are the seismic amplitudes, the median amplitude of all the stations adjacent to the river are the red dots. We're only showing them at night. That's why there are these breaks, because there's an adjacent road near this study area. So there's lots of cultural noise during the day. But the nightly values vary pretty smoothly with discharge, and they don't really respond strongly to the gravel augmentation events. In contrast, the high frequencies shown down here, one for an upstream segment and two for a farther downstream segment. These show big peaks after each of the gravel augmentation events, the dashed black lines, and then decay afterward. The minimal values after the gravel augmentation events are still much higher, about twice as high in the upstream half of the reach versus the downstream half. And just to show you the halves of the reach, how this is being separated, segment 1 was above this dashed white line, and what you see in the channel is the differential bathymetry. It shows us where the channel was actively changing shape during the flood. And so we see the very high seismic amplitudes, the size of the symbol and the color of the symbol for the nodes is showing us the strength of the ground shaking during that time. And so where the bed's actively being modified and the transport rates are higher, we're seeing much higher seismic amplitudes. And then just a couple hundred meters downstream, we're seeing much lower amplitudes where the bed is not actively being modified. Let's get through that. And so it gives us a chance to look at how this compares. That Tsai et al. Model that I mentioned earlier was a model for a bedrock river. So having rock impacts on a hard elastic base of the channel, not an alluvial bedded river, in this case a gravel bed river. And so what was interesting is that the model predicts that if we use the sort of 94th or 95th percentile grain, somewhere between the D90 and D95 values here known for the Trinity River, this should predict the spectrum during the times of peak transport. And instead what we see is that the observed spectrum, the black one's about 20 decibels lower, 15 to 20 decibels lower over the part of the spectrum where it's strongest. So what's interesting here is that it's probably giving us some way to start working on quantifying from outside the channel with seismology how much the work on the channel boundaries is being diminished by having the protection of alluvial cover compared to a bedrock channel. So time management here was not outstanding. The two topics that have focused on for kind of very different uses for these dense geophone arrays. One of them to look at local seismicity around a volcano, and also to sort of leverage that array to also apply it for crustal scale active source imaging. Was a great dual benefit of having the dense geophone array and these very portable instruments. We could also apply it at much smaller scales to look at environmental signals such as bedload transport. I just want to mention a couple other things related to geophone arrays and some of the studies coming out that you'll see, and some of the resources. There's an upcoming focus section in seismological research letters on dense geophone array seismology. Papers have been submitted for that, and so a big batch of papers doing all sorts of creative things with dense geophone arrays will come out this summer. So if you're interested, keep an eye out for that. And the IRIS Pascal instrument pool has, for the past year and a half or so, had about 60 of the 3-component 5 Hertz geophones with a 1-month battery life. And future growth of that facility isn't exactly known at the moment, but is a goal. There's been very high demand for it. The main point perhaps is that it's possible to get your hands on these through community resources if you're interested. Also through community resources, there's a lot of this type of data available at the DMC. The St. Helens data and the Trinity River data that I showed today are both open access data sets. There are a number of other data sets around things like crustal fault zones and all sorts of different settings. So there's a lot out there if you want to get into it. With that, I'd be happy to take any questions, and just appreciate the support for this research from the National Science Foundation. Thanks.
Thanks, Brandon. It's a very interesting talk. Folks listening out there, if you do have questions for Brandon, please feel free to send those in now, and I'd be happy to pose them to Brandon. We've got a handful of minutes here for some Q&A time. While we're waiting for those questions to come in, I just wanted to ask Brandon if you could quantify a little bit how many nodal sensors you used in each of these 2 deployments that you talked about, and if and how you would have potentially used more sensors if you had them available.
So for the Trinity River example, there are actually 4 different arrays. I just showed the biggest one. So there are 4 different sites where they measure gravel transport. And so I wanted to have some seismic recording at each of those sites to look across a broader parameter space, because the flux rates and grain sizes change. This was the biggest one. I think it had 76 nodes in it. That was pretty effective, although when trying to back project these data into the channel, we found that even with 30-meter spacing, if you're trying to back project, say, 20 to 50 hertz signals, you need a very good velocity model and very dense spacing. But I don't know that I'd go with a lot. I don't know that I'd go with more in this setting. I think this one's pretty well covered. At St. Helens, the number was really chosen based on the maximum amount this team could deploy in about 4 days before the shots started, and the maximum number we could rent on a given budget. Where you could improve this array is having spatial coverage that's not strictly limited to the trails in this sort of spider web shape. That could improve it quite a bit. We have, say, 300-meter spacing along the trails, but then often big gaps between different road or trail systems. So I think in terms of a large volcano setting, you could potentially go very high with the number of sensors around in order to get good 3D images.
Okay. We've had a few questions come in here. Rick Astor is curious to know if there's any chance of beamforming using the Trinity data?
Yeah, so that's a good question with the Trinity data. So we can think about beamforming in different ways. Often we think about using a little array that's far away from the source, and so we could assume, say, a propagating plane wave with the Trinity array geometry. More likely, we could do a similar thing, but we wouldn't be able to assume plane waves. We'd have to, back project circular or spherical wave fronts from each of these stations and project those into the channel. And I have done that, and so far I can confirm that the signal is coming from the channel, which is perhaps a little underwhelming. The river is bright red, and the area outside it is much, looks like a weak source of energy. So most of the channel actually looked pretty steady in this experiment. We didn't see things like a pulse that, say, swept down the whole channel. And that may be a little surprising since I talked about these bed forms moving. But if you look at some of these bed forms, say this little crust, this red area here, this bed form moved a total of about, I think, 20 or 30 meters over 3 days. So it's not going to be a very rapid or large movement. It's moving basically the equivalent of one of these station spacings at the most, and for many of them less than that. So we can back project the signal into the channel, and that's something I'd like to work on more. But so far, it tells us kind of what this visual view with the dots does, that the amplitudes are really high in segment 1, and that the signals are coming from the parts of the channel that are seeing the most change in their bed forms.
Bouncing back to St. Helens here for a minute, we had a question about the STA LTA images you showed for the Mount St. Helens earthquakes, and it looked like they all moved rapidly upwards with time. Were the videos real time, and could you explain the upward motion that we saw in those animations?
Yes. So let me get this going. Great. It stopped. Why did it stop? Okay. So what you should be seeing, if this worked perfectly and we had the earthquakes covered from all sides, it's definitely a big array and we have good coverage. But notably, we don't have anything over the top. So if you're looking at the upper surface of the mountain in this image, we'd start to get some nodes just on the right side of it and a little bit on the left, but none over the top. So what you should see is sort of a collapsing circle in cross section. It should look like this sort of circular wavefront, and then it should eventually collapse to a point and disappear. And in this case, as we're playing the data back from the stations, it's coming up from below. It reaches its maximum amplitude somewhere, but then lower amplitudes continue up toward the surface. So you get some energy that if you're back projecting the signal from all the stations, each station is going to send out its signal in all directions. We're just showing where it stacks most constructively. So here we see them come up from below because these are all refracted P ray paths that are going out to the stations off to the side. So they're coming up from beneath these events, hitting the event, and then the signal should start to get weaker as it moves up toward the surface from there.
So for these event detections, you're assuming that the seismic energy is mostly P wave?
We are using vertical component data, and we are back projecting it through a 3D P velocity model from Waite and Moran 2009 is what was used in this case. So by back projecting along the P travel time curves and using vertical component data, the signal should be dominated by P. We've done this for the deep long period earthquakes using both P and S signals because they produce pretty big S arrivals even on the vertical channels. And so you can do this with multiple phases at the same time if you want.
Okay. bouncing back to Trinity here, had a question come in from Tim Bartholomew about the mismatch in the Trinity River spectra from observations from the SCI 2012 theoretical model. He says, I like the couching of the mismatch as the alluvial bed absorbing some parts of the spectra. Are you aware of other new developments in understanding the source and path effects of these signals?
Other new developments that let me get through. So for the source effects here, I mean, the spectrum that I'm showing is just the spectrum during peak transport. And so it should have some component of turbulent flow in the water column contribution. That seems to be dominantly at the lower frequency end. If we just looked at the differential spectrum during constant discharge when gravel was added, shows us that above 20 hertz, above 15 to 20 hertz is where the bed load is dominant. So there are complications definitely with that change, even though we're adding bed load at that time. It's also perturbing things like the shape of the channel, and so it can have feedbacks with turbulent flow. But in this case, we know the shape of the channel, and so I'm not as worried about that. The shape of the channel is kind of this alternating bar format. This is before the flood and gravel augmentation, and on the right is after. The bars get inflated a little bit on average. They grow a few tens of centimeters, but the sort of relief in the river before and after is still right about 3 meters. And the changes were more on the order of, say, 20, 30 centimeters or less in most places. So the specific shape of the channel was not dramatically changed. The other thing that's happening in these spectra, or one of the useful aspects of it, is that they're averaged over something like 35 nodes in the upstream segment that has the highest transport. So if there was a more dramatic but very local change, say scouring out one pool or one small area of the channel, that change by one seismometer wouldn't dominate the whole change in the spectrum. So I think overall that the power is a lot lower than we expect for a bedrock model. It's probably pretty reliable. That's because this is not a bedrock channel and that it's blocked by unconsolidated gravel. But there's definitely a lot of detail in here to actually modeling what's going on in these interactions of a dynamic gravel layer at the base of this river and the turbulent water above it.
So we have a bunch of additional questions come in. I don't think we're going to have time to get to all of them, but we did have two that I wanted to kind of combine and put to here, having to do with data analysis. First, a question about if you could speak to the uniformity of time series between nodes for applying workflow processes like STA, LTA, and does it require a lot of culling, or is it readily digestible at large numbers of nodes? And somewhat relatedly, are you aware of any available community available software packages for helping one handle the huge amount of data coming from these arrays to do some of these standard types of processing like event detection, back projection, beamforming?
So I think handling the data coming from these arrays, this is something a number of people are still actively working on. So I would say if there's a method out there that you're interested in, they're largely still at a pretty homegrown experimental level, and so contacting those people would probably be the best move. Moving toward a repository for some different types of tools sounds like a good idea. In terms of uniformity of the time series and sort of how to handle, say, culling of the data, things like that. One of the main things that we did was whenever we're stacking, we're not using a linear average, we'll use a median. If we're looking for a magnitude -1 earthquake, a few elk walking around near seismometers is much, much louder than, orders of magnitude louder than any, say, magnitude -1 earthquake beneath Mount St. Helens. And so these back projection images and other types of detectors that we've used ended up being much more stable if we were using a median rather than a mean. So some simple sort of nonlinear tricks like that are helpful for identifying outliers. There are certainly more sophisticated ways you can go with identifying outliers in the time series. But if you just look at a random 2.5-minute snapshot, most of these little earthquakes show up pretty well. There are some traces that are obviously higher noise than others. There's got to be some signal going on around those sites. But there aren't too many that need to be thrown out. There are enough traces, though, that it practically needs to be done in a quantitative manner, some automated manner, and not by hand. But we found the data quality overall to be pretty good. There were some stations we manually did have to sort of boot out of our analysis if we know that, for instance, we found them and they were knocked over on the ground. And if we look through the time series, we can find out when they were knocked over. We could decide when to stop using those data. And it was a small number, maybe 10 or so of the nodes that were most likely kicked over by elk during the experiment. So that's just a flavor of some of the things that you might have to deal with. But you try and get past needing any one node. The idea is that each individually is expendable, and that most of them will have good data, and that's fine. If 90% of them have good data, then we're all set, and we just need some way to efficiently remove the others.
Great. Well, thanks again, Brandon, for a very informative and interesting talk. Folks out there, if you do have additional questions, or if I wasn't able to get to your specific question, I would encourage you to reach out to Brandon via email. I'm sure he'd be happy to take questions and respond to people that way if you still have questions. So thanks again for tuning in. Thanks everybody for being here, and stay tuned for future IRIS webinars in the future.